as is ritual, I'm going to double check the audio. And then as is ritual. All right, cool, we're good. Welcome to the stream, everybody. For those of you that are watching live, the live chat of the stream is always free for questions. For those of you that are watching the recorded video of this, you can either ask a question in the comments of the video once it's posted, or you can come into our Discord. The link is in the description, and you can come ask me all your questions. So, this week we are building off of the knowledge that we learned in the last few sessions. The main topics this week, we're going to talk about threaded programming. So we're going to talk about what it means to have a synchronous program, what it means to have an asynchronous program, and we're going to use those topics to then start talking about web applications. So we're going to talk about HTTP requests and how those work with APIs. So, the first topic that we're going to talk, okay, actually a preface. All these topics do get really complicated and really advanced. I'm going to take you guys through the absolute bare bones of what you need to know to just get started. There's a lot of caveats when working with these things. If you go try and even change a little bit of the program that I've uploaded to GitHub, I should have mentioned that at the beginning of the video. Um, all of the code for each of the tutorials in the series are up on GitHub. The link to that is in the description, so you can get all the source code that we're working with. You will have the source code in the state that we start the video with. If we make any changes, I'm not going to upload those because I want it to be in a clean state. So, what is threading? We're going to start with threading, right? So, in our program right here, I just have some commented out methods that we're going to call. Since this topic is so complicated, I kind of wrote myself up some notes and I pre-made some functions and whatnot because I want to make sure that I'm not leading anyone astray because even me like just misstating one sentence could throw you off. Because this stuff is really complicated. So I spent like 6 hours this week making sure that this talk was ready to go. So what we're going to do to start is I'm just going to pull open a Microsoft Paint, and we're just going to draw something real quick so we can get your head visually wrapping around what's happening. So when we talk about threading, what happens is when you start up a program, you have a thread, right? We'll call it M for main. In the main thread, whenever you start up an application in C#, in the first video we talked about the CLR, or the Common Language Runtime. All C# programs, all Visual Basic programs, all F# programs, all run on the same runtime. And a runtime is basically like a process that runs on your computer that says the code that you've written that's been compiled can execute on my runtime. And so, like, if you create a variable, the runtime says, "Oh, hey, Mr. Operating," like it operates as an interface between your code and the operating system to make these requests to do things. So one of the nice things that the Common Language Runtime provides for you is the capability to do threading or multi-threading. Multi-threading basically just means if I have a main thread, right? Whenever you start up any process in on the Common Language Runtime, you have a main thread, and so in a normal program, like if we just go look at we'll just take this program for example. In the main method, if these weren't commented out, these would go line by line and it would execute this line, and only once this entire method that we've called is done, it would execute the next line, and so on, right? Until it gets to the bottom. And then when we reach the closing curly brace, the main method is now over and our program is done, right? So the common language runtime says, okay, now we need to start our shutdown process. Do we have any threads running? If we do, let those finish before we shut down. Otherwise, it'll just shut down the program, right? And I'm sure you guys are all familiar with how starting up and shutting down a program works. For example, Visual Studio itself, the program, if I hit the X button in the top right, that would close the process that's running, right? So the way threading works is we have a timeline, and on there we execute tasks, right? So a task would take up like a chunk of time, and then the next line of code will take up maybe a smaller chunk of time, and so on. And these things are allocated on the CPU for them to be processed, right? And so what happens if we want to run two things at the same time? Or why would we want to run two things at the same time? Well, let's say we're going to get to this topic much more in detail later, but let's say I'm google.com, right? I am a web server that you can hit. By hit, I mean you can make a request and it'll give you a response. Well, when you request to go to google.com, if two people made a request at the exact same time on a non-multi-threaded computer, there's two options. Either A, it could just disregard the second request because it doesn't know how to handle it, or B, it could put them in like a queue and it would just execute them one at a time, right? Well, if we can start up another thread, we can just call it thread one. Well, then we could have items executing on this thread at the same time, right? So they're basically just separate timelines. Um, on most CPUs, the way it works is that you're just going to have one core, right? A core on a CPU is just a logical unit that says I'm doing things on my own. I am capable of processing things. I am capable of doing arithmetic, addition, subtraction, those type of things, and I'm capable of interacting with RAM and your hard drives and grabbing memory, doing operations on the memory, and then storing it off somewhere. So the beauty of threading is that you're allowed to do these things at the same time, right? So if two people request to go to google.com at the same time, well, the main thread could start processing, and then thread one could start processing, and whenever they finish, right? Um, so the first thing that we're gonna start talking about is just what is a thread, right? So in C Sharp, we're gonna start with this thread basics class that I've made. Don't worry about any of the code yet. We're gonna kind of talk. There's a lot of conceptual understanding that you have to have before we can even get into it. So C Sharp supports parallel code execution, and parallel means they run at the same time, right? And they support that through what's called a thread. A thread is basically an independent execution path, right? So independent execution path basically means a separate timeline, right? And it can run at the same time as others. And so when the C Sharp program is started, the CLR starts the main thread, right? Whenever you start up any program, you have the main thread, right? If you have like a UI in your program, right? Like let's say your I don't know, Discord, for example. It has a main UI thread, and maybe if you want to go like search for a bunch of messages, well, it would say, let's go search for those messages on a separate thread. So that way, like, you could click on the UI and still do things in the main thread while the other thread is trying to do that search thing for you, right? And that's if you don't have threading, right? If you start a process, you have to wait for that one to finish before you can do something else. And when you have UI based applications, right, when you're trying to do things, right, like imagine if I was in Visual Studio just trying to highlight something. Well, if it was, I don't know, compiling my project, or if I hit run, right, imagine if I couldn't touch anything while that was happening. That would just completely wreck the whole purpose of having a UI, right? You want to be able to have things happening as you're trying to interact with the UI, right? So that's one of the main examples I can think of how multi-threading is useful. So you get these threads by requesting it from the operating system. So the common language runtime handles all these things under the hood for you. You don't have to worry about how it happens, right? You don't have to worry about you know what happens when the thread ends and those type of things. The C Sharp handles that for you, or the common language runtime handles that for you. So the other thing that I wanted to talk about before we get too deep into it is you have a thread pool, right? So by default on your computer, if your computer has 4 cores, you're going to have a thread pool of 4 threads, right? It's literally, think of it like a pool, like a a physical pool, right? You can pull things out of the pool, or you can put things back in the pool, right? So the common language runtime kind of examines your hardware on your computer and decides what this pool is going to be made up of. For each core, you're going to have 2 different types of threads. You're going to have a worker thread, which would just do normal operations, right? You could go do a search or whatever. And then you'd have an I/O thread. I/O meaning input and output. So if you want to read or write from a file, read or write from a USB drive or a hard drive, anything that has to deal with input and output, even like reading from a network card would constitute I/O. So you're going to have 2 separate different types of threads here. So a thread pool has 2 functions, right? You have to maintain a queue of the work to be done, right? If 100 people request to go to google.com at the same time, if I only have 4 threads on my computer, well, I handle 4 of them, and then when these 4 get done, I handle 4 more, and so on, right? So I have to have a queue. Think of like a line at a grocery store, and you handle people as you can, right? The second function of a thread pool is to hold a collection of threads to do the work, right? So it has some sort of scheduler to schedule which thing to pull out of the queue, and when this thread is done, what's the timing, right? So if we just go look at how threads work in C Sharp, thread, the class, comes from system.threading. We're looking actually at C Sharp now, right? So thread comes from system.threading, right? System being coming from the .NET Core, and threading being the library that holds all of the threading functionality. So what we want to do is we want to tell that thread what to do, right? We have this new timeline. What do we want to do with it? Well, we want to execute a method on that timeline, right? So we create the thread and tell it which method it's going to call. In this case, it's just called task1, and all it does is print to the console task1. I'm actually going to close everything out so you guys don't get overwhelmed. Let's keep it as simple as possible. So when we create a thread, all it does is it requests, it says, Mr. Common Language Runtime, will you ask Mr. Operating System if we have enough space left on our cores to allocate a new thread? And you have to think, you remember when we were talking about the call stack previously, right? If we go back to our paint, well, if we're on our main thread, this has the main method, right? If we go back to program, we have our main method, right? And then if I uncomment this guy, this is the one they're going to be working on. The start thread method would be put on top of that, right? So any local variables that are inside the start thread, when the so this would be the main method, this would be the start thread method. Inside of this like frame in the stack is going to be all the data for all the local variables, right? And then when this method is done, we pop it off the stack and say all of these variables can be collected by the garbage collector. We no longer need to hold them in RAM, and then we go back to the main method when it's done, right? Well, in this start thread method, what we do is we say, let's create, sorry, wrong file. Let's create a new thread. So what does that do? It basically creates another timeline, and we'll just call this T1 for thread 1, and it has a call stack of its own, right? So we create the thread. It has some memory overhead just for creating the thread, right? You have to say, hey, Mr. CPU and operating system, will you store this in RAM and say that I have another timeline executing? So there is a little bit of overhead, right? So it's like, if you're just trying to say, I want to do 1,000 things in a row, and your computer only has one CPU, doing it without multi-threading would be the fastest way to do it. If you have, let's say, 3 things to do, and you have 2 cores, well, do you really want to do you want to just do all three things in a row on one thread, like on the main thread? Or do you want to create 2 separate threads and say, handle those 3 things as you come? You probably wouldn't want to do that because doing 3 small, quick things would actually be quicker than having this extra overhead of the next thread, right? So when we create this new thread, what do? We say we're going to start the thread. So we want to start all the tasks that are on that thread. In this case, that task is just task 1. So on top of our call stack is going to be task 1, right? Oh my gosh, I should have picked something other than T1. Thread and task, whoops. But anyway, so when task 1 completes, right, it's just going to print out to the console, right? If we go down to task 1, all it does is just do a console.writeLine and just prints task 1 to the console. When that's done, this guy's going to be popped off the stack, and then there's nothing else for the thread to execute, so we don't need to use this thread anymore, right? I mean, the thread may still be allocated by the common language runtime, but there's no functionality happening on this timeline anymore, right? Okay, so then what do? So we create the thread and say we're going to do something on it, and then we start the execution process. And so the cool part about this is while this thread is doing its things, we can do we this is gonna if you're somewhat beginner of C sharp, this may kind of blow your mind. But in normality, what would happen is you execute this line. You don't execute this line because it's a comment. You execute this line, and you have to wait for whatever this task 1 method is to be done, right? Well, the beauty about threads is since this guy is on its own thing, we just keep executing, right? So I created another thread and I called it parameterized thread. And instead of doing the method called task 1, I said task with param, because we're going to pass a parameter in, right? So if we go look at task with param, it takes in an object and it prints it out. Since it is a task, all tasks handle objects, or a thread takes a parameterized thread start, which uh, is basically a delegate that is a method that's going to handle this execution when we tell it to start, right? So you can see in the start method, I pass in the parameter to that function. So this looks a little funky. Like normally you would think it would look like this. I would pass in the parameter to the method itself, right? Um, but as you guys saw last week in the lambdas and delegates talk, if you, similar to like a delegate, remember how we passed methods in as parameters, right? And we don't have to add the parentheses like we are calling a method, because we're not calling that method. We're passing this thing in as a parameter. And so now this thread can activate that method or run that method when we tell that thread to start operating, right? And so we can't pass in the parameter when we create the thread. We have to pass in the parameter when we start the thread, which is almost beneficial because, maybe something happens in between when we create the thread and when we start the thread that would change the parameter that we want to pass in, right? So you can see all task with param does is it does the exact same thing as task one, but rather than printing out task one, it prints out whatever we passed in. And since it takes in an object, we just inherently cast it to a string, right? So if I wanted to explicitly cast it to a string, I would put string in parentheses, and that says, you know, output, I know you're an object, but I want to force you to become a string so that I can print you, right? Um, but since WriteLine is expecting a string, C# understands that, and you can leave it off. I feel like there's a name for that I'm missing. It's like auto unboxing, something along those lines. I'd have to look it up to have the correct term for you guys to Google. If you're interested in that, just ask a question. Okay, so what am I trying to show off here? We're going to start one thread, and it should print out task one. We're going to start another thread, and it's going to print out thread parameter, because I want it to just print out the name of the parameter. And then we're just going to do a console.WriteLine for test at the end, right? So if we just go ahead and, okay, so the method is called start thread. In program, we uncommented it out. So at the very top level, it's going to enter into our function here, and then in that function, it's going to start threads, right? So if we just go ahead and hit run. Okay, so what happens? You can see, man, this looks so weird, right? I have this console.WriteLine test, and it should be the last thing that executes, right? It's the last line of our method, but it's actually the second thing that prints. So you can see it printed out thread parameter, test, and task one, right? Those are the three things that we were supposed to print, right? Because this guy is supposed to print task one, this guy is supposed to print thread parameter, and this guy is supposed to print test. So you can see the order isn't guaranteed, right? Just because I told this thread, the task one thread to start with, doesn't mean that it's guaranteed going to finish first. Whatever the CLR decides, maybe I had, if we were doing this in a different context, maybe task one takes a long time to finish, right? So it could be last, which is awesome because that allows us to send these things off, and whenever they're done, right? Does that concept make sense to you guys?
Yes, mate. But in this particular example, why did why was the order the way it was? Because they're all basically doing the same thing, aren't they? They're not like it's not like one is particularly heavier than the other. Do you know what I mean?
Yeah, and that's a great question. I assume that test. I had personally assumed that test would be the first one to print, right? Because creating the threads is going to take a little bit of time, right? But as far as task one and task with param, it looks like for whatever reason, if you pass in a parameter, I don't know if that's the reason it's faster. I honestly couldn't tell you because this is happening under the hood, right? It's kind of handled for me, right? So what we could do is we could put a breakpoint right here. And if we hit run and we hit the breakpoint, you can see down here, we have the main thread and we have a worker thread, right? We're not doing any IO operations, right? So there's two different types of threads, an IO thread and a worker thread. Our worker thread, you can see in this case, it doesn't have a name or anything, but you can see the location is task one, right? That's the thread that is happening. And it hasn't printed anything out yet. I almost want to put like a couple of these console.WriteLines to see, if at one of them, depending on which one of these guys is finished. Um, I don't know. It's a really great question. I think it would take a lot more research. Like the beautiful part. Okay, so for those of you who don't know how to get to this threads window, if you go to debug Windows uh, threads, it will pop open this window, and it'll pop open like out here or something. And so what you do is you click on the top of it and you drag it to the window that you want it to, and then you put it in the center of it, and then it'll add it as a tab, right? Um, so yeah, it looks like the task with param thread isn't even on our it's not even like a managed thread yet, right? So I'm actually kind of curious. Let's see if it finishes in a different order this time. Okay, I know what happened this time. I did not close out of the console. My bad. If we run this time, you could see task one finished first and thread parameter finished second. So it really just depends on what the status of your machine happens to be when these threads are created, right? There's no guaranteeing which order they're going to be built into, unless you are looking at the very like low level commands at what's happening, right? I hope that makes sense.
So you didn't change anything in the program, right?
Yeah, if I just hit run, we can see. Ah, goddamn, I didn't close out of the console. Okay, you can see it's thread parameter and task one and then test. Completely different order.
Fair enough.
So it really just depends on how the CLR feels like handling it, right? Or if we have a lot of RAM and one of these processes is going to take up a lot of RAM, maybe it's going to put that one last and see if we have less RAM when we want to try and execute it, right?
Yeah, I guess in this example it doesn't really matter, so it just kind of picks any of them.
Yeah,
Yeah.
that's what it appears to be. Yes. Okay, so we're going to look at other ways at which we can start threads. So maybe okay. So the difference between I'm going to clear these up really quick just so it's abundantly clear what's going on. So maybe we don't need access to the thread once it's started, right? In this case, we could just say we want to declare a new thread and tell it to start, right? We don't have to save it to a variable, right? So if you don't need to do anything with the thread, you should just tell it to, hey, go start this task. I just want to directly start you. I don't care about telling you what to do afterwards. This is another way to do it, right? Um, Now we're going to look at lambdas, right? Instead of passing in task one, maybe we want to just write what the function does here, right? This These two functions are equivalent other than the fact that this one is going to print out task 1 and this one is going to print out lambda thread task. The last way, this is the same way as the first one, right? We create the thread and we tell it to start. And then there's some properties on threads that we can change. We can give threads a name, right? So when we were looking at, if I go back to, hold on, let me undo my changes here. If I go back to looking at this debug, you can see that threads have a name, right? You have the main thread is a default name, but if I don't give it a name, it doesn't have one, right? So if I give my threads name, that can help me with debugging, right? So if I go back to down here, if I just name it like my new thread or something, that helps me with debugging, right? I can see what the name of that thread is. So if I want to like give my threads a number, like their name could just be 1, 2, 3, 4, whatever. So that way you kind of know what order they started in. That might help you because when you do threading, you get what's called race conditions, right? Like if your operating system happens to execute one thread quicker than it happens to execute another thread, weird things can happen. Okay, so the other thing that you can do with a thread, so you can set its name, right? So this is just used to identify, I guess not the currently running thread, but whichever thread you're inspecting. Sorry, that was some poor wording. You can set the thread to whether or not it is a foreground or background thread. So by default, if you don't set is background, it's a foreground thread, right? So if I set is background to true, then it is a background thread. If I set it to false, then it's a foreground thread. A foreground thread is a thread that's in the foreground, right? It's like in your it's like in your face, right? Whereas a background thread, really okay. So the only functional difference between them is that if I close the application, background threads don't keep the application running, right? They're not I don't background threads would be like, I don't really care if this finishes. It was just something that needs to happen, right? Like if okay, let's say I'm google.com again. I like using this example because it's something that everybody knows how to do. If I go to google.com, right? If I hit enter and 100 other people hit enter at the same time, and those are background threads and google.com's servers crash. Well, they can just crash, right? It doesn't matter. They don't need to send me a response. That's not a high priority thing, right? It's not like they're like saving like payment data or something like that will actually have a monetary difference, or maybe it is a priority for them, right? So like, let's say before our server is about to crash or shut down or whatever, we want to make sure we send that Google.com response back to them so they have access to that web page. Not that they'll be able to do anything with it after the server's crashed, but you know. So if it's not a background thread, then it would prevent the server from shutting down until that thread is done, right? The common language runtime will still be a process that is executing on your computer until that thread is dead. And then you can set the priority of a thread. So this is what we could have used to order these threads better, right? So if if we wanted the parameterized thread to have a like okay, so the common language runtime has like a scheduler that looks at these threads and has like an abundance of algorithms to determine why it should give one time on a CPU core, right? Well, if we give it a higher priority, um, so there's a term called heuristics. Heuristics, and basically what heuristics means is, um, the most simple example I can think of is I'm a car and there's three roads I can take. uh, which road should I take, right? One heuristic or one way of determining which route is the best to go would be how far is it, right? What is the distance between me and the um, destination depending on which road I take? Another heuristic would be what is the terrain, right? So heuristics are used to determine why you should pick um, uh, why you should pick one path over another, right? So a thread priority is a heuristic that would tell the task scheduler this guy should be executed first over other threads because it has a higher priority for whatever reason, right? It depends on like your language or your business rules, right? So like I don't know. If we're thinking of Google again, maybe Google Images requests have a higher priority than just Google.com. So they could set their thread priority to higher so that way those requested always finish first for whatever reason, right? Okay, that was threads in a nutshell. Does the concept of a thread and how to create one and run it make absolute concrete sense?
Yeah, it does at the moment, definitely. Yeah,
Alex?
Yes, at the moment it does.
Perfect. It
but
will
I
not in
guess it's
about
still
10
a bit.
seconds. Yeah.
Yeah, yeah.
Okay, so I did have all these functions commented out, and we can run them. They're all going to do the same thing, right? They're just going to start the thread and run whatever function that is inside of the thread's construction, right? So I'm not going to go through that because I think that's pretty self-explanatory. But I included them in here so that if you did want to run them when you download the project from GitHub, you can see what they do. Okay, on to some threading examples. So this next one's pretty cool. So we're going to look at just this one function called getPCInfo. I'm going to close out everything else so nobody gets overwhelmed. Okay, so what does it do? We create two integers, and you guys may not have seen this syntax before. I didn't show it previously. These two statements are equivalent, right? I can declare them as integers on separate lines, or I can just put a comma in between them and say, I want to declare that this is going to be a reference to somewhere in memory, and that spot in memory has the size holding an integer, but they're not set to anything yet, right? Well, I guess since they're integers, they're primitive type, so they'll be set to 0 or some default value. So what are the values that we have? We have the minimum worker thread count, right? So the minimum number of worker threads that our computer will that the common language runtime will support on my machine. We have the minimum number of IOC threads. IOC is input output control thread. I forget what the C stands for. I know it's IO. IO is input output, right? So remember when I told you guys earlier we have two different types of threads, a worker thread and an IO thread. And then, since we have access to system, we can access our environment, right? So if we hover over environment, what does it say? It provides information about and means to manipulate the current environment and platform. So .NET gives us a way to look at our environment. And what do we want to look at? The number of processors that we have on our current machine, right? So if we want to go into system.environment, we can see what other things it allow us to access. We can see our operating system version, whether or not it's 64-bit, and so on. So these are kind of some cool things to see that .NET is cross-platform, right? If I were running this on a Linux machine instead of a Windows machine, it would let me know my operating system version, right? It does depend on which version of .NET you're running. In the first video of this series, we talked about .NET Framework versus .NET Core. .NET Framework is for Windows. Some of these things would be inaccessible. .NET Core is meant to be cross-platform, so these things would work on, Mac, Linux, Windows, all their versions. Maybe not all of them. There might be some caveats. I am unsure of whether system.environment is accessible in .NET Core and .NET Framework. So don't ask me. Okay, so we get our number of processors, and then we have this thread pool thing. So before we talk about a thread pool, we're just going to run through the rest of this code so I don't leave you guys hanging. So the thread pool, this is our pool of threads, right? So this is a static class, right? If we hit F12 on it, it'll take us to where it's at. It's in system.threading. It's a class called thread pool, and it's static, right? So we can't create an instance of it. It kind of handles things for us. So you can see the number of threads that we have, how many completed items there are, and so on. You can go look at other methods. But the one that we want to use is get the minimum number of threads, right? So we want to get the minimum number of worker threads and IO threads that our processor will support or that our thread pool will support based off of the hardware that we have, right? And then all we're going to do is just print that out, right? So if I go back to program and I hit run, this is just going to do my get PC info. I didn't close the console because I can never remember that. Okay, so it says I have 8 processors, right? Well, if I just go to right click on this PC and go to properties, you can see I have an 8-core processor, right? So it counts each core as a quote unquote processor, right? Because each core can process information on its own, right? So for each one of our processors, or in this case cores, there's one worker thread and one IO thread that it supports, right? So there's a total of 8 for each. Okay, so that's a good example of why whenever you go look at like CPUs online, they'll be like, oh, it's 8 cores and 16 threads. Well, that's because we have 8 cores and 2 different types of threads that you can have, right? Fun fact. Okay, so now we're done with get PC info. Now we want to run some threads. And I have a bunch of stuff commented out here. And we can just delete it to keep you guys without all the excess stuff. So this is just a static function, right? Which means from program we can access it without creating a class. So we're just going to call run threads. And so what does it do right now? It on the main thread, right? So if I don't create a thread until to start things, it just runs that function on the main thread, right? And it's going to run this function called write x. And all these write functions, all they do is they loop from 0 to 1,000 and writes that letter 1,000 times, right? So write A writes 1,000 A's, write W writes 1,000 W's, and so on, right? So my goal here is to show you that this will write 1,000 X's, and then it will create a new thread, right? So I'll go ahead and read my comments. We're gonna create a new thread. We're gonna call write y on that thread, and then the common language runtime is going to assign each thread to its own memory stack. We talked about that, right? It has its own call stack. So the local variables have their own scope, right? So that way, we can't access the, for example, the int I, right? Int I is not going to be accessed in write w because it's it's in between these two curly brackets, right? This is its scope, right? It does not exist outside of this function. Okay, so we're gonna create a thread y and we're gonna start it, and we're gonna create a thread z and start it. And what we're gonna see is something somewhat mind-blowing if you haven't seen threaded processes work together. So what happens, right? We print out all of our x's, we print out all of our z's, and then we print out all of our y's. Well, that's weird because we said we should write y's and then write z's. Well, this is kind of the problem. This is kind of the problem that we ran into earlier, that the operating system or the common language runtime decides when these things should happen, right? And if you rerun it, it might be in a different order, right? I've had it so that it will intermingle. Gotta remember to close it. It'll intermingle the y's and z's, right? Hold on, let me back up. If we start them closer, that might increase the odds that they overlap. In this case, it doesn't. Okay, so what I wanted to show you is that if these things happen to want to be running on the same, okay, so let's say our processor only has one core, right? What it will do then is what's called time slicing. It'll say, okay, you, Mr. Thread, you have, based off of your priority and based off of what you're going to do that has some sort of heuristics for it, you're allowed to have this much time on this core. And after that amount of time, we're going to let something else happen, right? So in this case, it probably ran all 3 of them on separate threads. But if for some reason they happened to run on the same thread, then it would splice them, right? Maybe it would go z, 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 and then y, 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 and then back to z, 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 and so on, right? The common language runtime determines how that happens, but I wanted to show off the fact that just because, they are separate threads doesn't mean that one's going to finish at a different time than another, and that that one won't stop and start and stop and start and let other things happen. Because if a common example of, or not a common, but a cool example of this that I can think of is old Apache servers. They were web servers, right? So like Google may use, I don't know what type of servers they use, but they probably use something way more up to date than Apache. Apache was this old server that was written in Java, and whenever you made a request, right? So let's say, I don't know, I want to request a web page, I don't know, some web page. And on that web page is a bunch of data, like, I don't know, a bunch of data about users or customers or something. And when I make that request, it would start up a thread and start figuring out, it would go grab that data from the database and then it would return it to the user. Well, while that thread is running, what happens if, 100 more users come and request data? Well, if the CPU only had one thread, well, they'd have to wait until that guy was done, right? And then the next person would get to go, and then the next person would get to go. But it has to wait until the previous one finishes. Well, the beauty about the time splicing is that, you know, it would let one process start and then the other one could start like in the middle of it and do a little bit. And they could each just keep doing little chunks of work until one of them finishes and it no longer needs to do that work, right? Okay, so what are some other operations that you can do on threads? We can do a join. And basically what join means is we want to wait for that one to finish, right? So if we hover over join, what does it say? It blocks the calling thread, right? So whatever thread is calling the method write z, we want to block that thread for a certain number of milliseconds. In this case, 1,000. 1,000 milliseconds is just a second. So if we hit run, we should see that z always prints last now, right? Because it's going to wait a second. I didn't close that out of the console. I'm sure there's some setting for this. I keep forgetting. Okay. And z. I know I did it wrong. Okay, so since z, I'm spacing here. What am I doing? Hold on, let me go look back at my changes that I made. Just hitting all the hotkeys here. Is this code in the state that I left it? It is. Okay, I'm confusing myself here. This is why I wrote a bunch of things down. Hold on. Okay, so if we make this like 10 seconds, ooh, I have insert on. 10 seconds. Insert, please. I'm doing something wrong. I had this working. I changed the order of things. I don't know what I did. Okay. So you can't do join operations until you start the thread, right? Because you can't do any processing on it until. So another way to do a join would just be to, in the y method, I put in a thread.sleep, right? So what's going to happen is when I create this thread, let's go ahead and clear all these out so this isn't taking up a bunch of space. So when I create the thread, it's going to tell it that this method is the one that we want to call, right? And what is this method going to do? Well, when this thread is created, we're going to tell it to sleep for 1,000 milliseconds, right? So the thread, whatever thread that y happens to be on, we're going to tell it to wait for a second and then do whatever it's supposed to do, right? So if I run things in this order, y will almost guaranteed be last to finish because the actual function itself is told to sleep for 1,000 milliseconds, right? So you can see that, you see how there was like a pause between when z and y were printed out? It's because y is waiting for, a second. If I get rid of that sleep, and now I put back in the z.join, let me stop debugging, close the console. Now we're getting that weird functionality where you can see there's some y's and then some z's and then some y's and then some z's because the time slicing. Okay, join doesn't work how I thought it did. My bad. I'll have to look into that more. Perform stand-up and blocks the calling thread until the thread represented by this instance terminates or the specified time elapses. Right, so it blocks the thread saying you can't do anything on that thread, while continuing to perform standard COM and send message pumping. I wonder if console falls under COM. COM is like the old like Windows calls, right? So like if you wanted to like, I don't know, do something on like the actual like Windows system, that would be like com, as far as I'm aware. Okay, so even if I take out the join, right, we just start the threads, and now they're running at the same time. There's no sleep in between them. Not if I don't close the console. You can see that the Y's and the Z's are interspersed due to time splicing. Okay, so you could play around with this, and you could add in more of these. Another thing that I wanted to show was that if I put a non-threaded method after these guys, so write W just prints out W's, and I'd use different letters so that way you could see in which order these things are actually going. Like if they were all X's, it wouldn't work. But you can see now there's even W's inside of here, even though it's not a threaded method, right? So it's always going to write X's first because it's not a threaded method. This is on the main thread. It executes this entire function before it even looks at any of the next lines. When we get to this line, it's just going to create these variables. When we get to this line, it starts that thread. When we get to this line, it starts the thread. And since these two threads are running, we can keep executing the functions that are in this function, right? Like z.start happens and it says, okay, you're going to go off and do your own thing. I'm going to keep executing. So then it executes this line, right? And due to the way the time splicing is working on the CPU, you can see we have Z's, Y's, and W's mixed in depending on when the threads are allowed to actually do their output, right? Okay, I know that was I messed up several times inside there, and I hope I didn't confuse anybody more than I helped things make sense. Does that all make sense to you guys?
Yeah, man, I think I got it.
Yeah.
Okay, so now we're going to talk about the thread pool a little bit, right? So if I wanted to just like keep creating threads, what would happen, right? Well, we'd run out of threads to have when we hit 8, right? Like my computer can only handle 8. So the thread pool injects and removes threads every half a second. Why they chose half a second, I don't know. If so, the way their algorithm kind of works, there's two different parts of it. There's the time splicing, right? And then there's the hill climbing technique. And what that means is if they add a thread to try and help you handle the workload, and it doesn't increase the throughput, meaning it doesn't increase the amount of things that are happening overall, then it's just going to remove the thread, right? Because maybe you create another thread and that was too much overhead for the amount of RAM that it has, and now your RAM is full. Well, then let's remove that thread because that was too much memory that it was using. So let's do a little thought experiment. Let's assuming you're running an ASP.NET app. ASP.NET is the web server that .NET supports, and you're running it on IIS. And IIS is if you just hit Windows button and type in IIS on a Windows machine. Okay, I don't have it enabled, but what it would do is open up Internet Information Services. I forget what it stands for. Yeah, Internet Information Services. Cool. So it's basically a web server on top of Windows that you can start up, right? So let's assume that you're running ASP.NET on IIS. We're going to do that in our next video, by the way. And we're going to assume that your server has one CPU, right? So let's assume that there's 100 requests coming in, right? We're pretending our ASP.NET app is like a Google server, right? And there's 100 people trying to hit our website at the same time. So we're just going to assume that somehow, hypothetically, 100 of these requests came in at the exact same time. So if our one CPU has 4 threads, then the first 4 requests are going to be handled by the default 4 threads. Then after half a second, it's going to try and add another thread. And if that increases the throughput, then it'll keep trying to add more threads. So you can see how after because since it's half a second, right? Like I can think of web, like if I go to google.com, that responds, that sends the message all the way to Google servers, and I don't know, maybe it hits Boston or California or wherever their data servers are at, and it comes back to me in less than half a second. It's not sitting on their computer processing for half a second like it is in this thought experiment, right? So like the first 4 threads, or the first 4 requests are handled by the first 4 threads, and then after half a second it tries to add another thread, right? So to catch up to having, let's assume we can scale up to 100 threads. It would take, what is that, 50 seconds to even scale up that number of threads, right? Assuming that our requests are taking that long in the first place, right? So what do you do in that situation, right? This is where we start to look at asynchronous programming. So what we've been doing so far is called synchronous, right? Synchronous or parallel means things are happening at the same time, right? There's 2 separate timelines. Asynchronous means a is the prefix in English meaning not, so it's not synchronous. And so you may be thinking, okay, so we just did this cool thing that allows us to handle multiple different things at the same time. Why would we want to stray away from that? Well, so the main concept of async is that threads aren't blocked while requests are being handled. So those 4 threads that are handling requests would free up almost immediately as they're handling requests and be able to handle more of them. So we're going to go to Async Basics. So in asynchronous programming, a method is called that runs in the background, right? And the calling thread is not blocked, similar to what was happening beforehand, right? So like if in our thread example, this is our caller, right? The thread that whatever this function is the calling thread. It just so happens to be in the main thread, right? Like from the thread that write_y is on, I could in this write_y function, create a new thread inside of here, right? And this guy would then be the calling thread. So in asynchronous programming, and to an extent, just threading in general, um, whoever is calling the asynchronous function wouldn't be blocked, right? Like it would just keep executing as that method is doing its thing, right? And that thread will just run in the background, and then when it's done, right? And then um, whenever that calling, okay, so after you call the asynchronous method, the execution flow immediately backs to the calling thread and performs other tasks, right? So like immediately after I say y.start, it goes to the next line, right? So the 2 classes that you're going to see most used in async are thread and task. Thread is used for threading. Tasks is used for starting asynchronous tasks. So in the history of C#, there's been 3 asynchronous patterns that have been tried and have been worked on and reworked. The first one was the asynchronous programming model pattern. The second one was the event based asynchronous programming pattern. So we talked about events last time, right? Maybe, in that iteration of the .NET framework, they thought events would be smart. And the latest is called the task-based asynchronous pattern, right? And so we're going to be looking at tasks here in just a second. Um, Task-based asynchronous pattern is what's recommended to be used by Microsoft. The asynchronous programming model and the event-based asynchronous pattern were replaced by the async await pattern in C# 4.5 or 4.5. So if we go to Async Basics, you can see we're calling task.run, right? We're not starting a thread, we're just saying we want to run this task, right? So tasks use a thread from the thread pool, right? So a task is kind of a wrapper around a thread to do extra things. So when you say task.run, it's reaching out to the thread pool, grabbing a thread, and now we have a task with some extra functionality around it. So tasks can be run either in the current thread that you're on, they can be run in a new thread, they can be run in a thread from the thread pool, or they can even be run without a thread. I read that, didn't understand it, but I figured it would be useful to include. So we don't need to worry about the creation or the use of threads. The .NET framework handles the inner difficulties inside of how the threads work, right? All we have to do is say, hey, go run this thing, and when you're, as you're waiting, it'll deal with how it tells the operating system when to do things. So, okay, I'm gonna go to Paint and draw you guys another little example of this. So I'm going to draw a line in the middle, and on the left is going to be synchronous programming, and on the right is going to be asynchronous programming. And we're going to draw 4 timelines. And these 4 timelines are going to represent 4 cores on a computer. In synchronous programming, what would happen? We're using the context of HTTP requests, and the way they work at just a nutshell, we'll get to them in just a bit, is that you have a request and a response. And when I type in google.com and hit enter, I send a request to get the web page corresponding to google.com, and what they respond to me is the web page content, right? Like the HTML, the CSS, and the JavaScript. Well, in synchronous programming, what would happen is you make that request, and when it gets to the server, it does its thing. And the problem is that it blocks this whole core from doing anything else while that is happening. Whereas in asynchronous, when the request hits me and I'm the server, it says, okay, I don't care which thread you're going on, just put this process on a thread and have it do its thing, right? So this is gonna be its little time block. And in the middle of that time block, maybe this is some complex request trying to gather a lot of data. Well, in that time block, we could insert something else inside of this, and then it could be finished up at the end of it, and then send that request back to the user. The beauty of this is that there's no wasted time, right? The downside to asynchronous is the overhead of having to figure out which thread to put this on. The upside is that the threads are no longer blocked waiting on this really long request, right? So let's say, let's rework our example a little bit. Let's say a request came in, and it's going to take, I don't know, 10 minutes, right? So let's say we have this big block and this request is going to take 10 minutes. I don't know, maybe it's trying to grab weather data for the last 10 years or something like that. Well, in synchronous programming, this thread is now blocked for the next 10 minutes. Well, what happens if if 4 people make those requests? Our server can no longer handle anything else. It is just stuck, right? Well, if there was like a main or a UI thread, this would be awful, right? Because if the main thread was blocked, then you couldn't click on anything, right? You couldn't move while this thing is happening. Whereas in asynchronous programming, you may have this really long block, but what's going to happen is it's going to be chunked up, right? Rather than having it do this one long block, maybe it determines that, you get to do this much time, and then somebody else gets a turn, and then somebody else gets a turn, and so on, right? So that's the beauty of asynchronous programming, is that you never get blocked on one long process. The downside, again, is that the overhead of figuring out which thread is allowed to handle that, right? There's a little bit of overhead in calculating, maybe this thread has this much time and this thread has this much time. Which one should get to run this process? So that's why we are talking about asynchronous programming, because we're going to get to the point where we're talking about web servers, and almost every modern web server uses asynchronous requests and responses to handle, massive amounts of users. So in .NET 4.5, we introduced this concept of task.run. In older versions of C# in the .NET framework, there was other ways. There was like a task factory and one more that's not coming off the top of my head. But this is the modern way to do things. So we're just going to focus on that, so that way you really only have to focus on one thing. And while this may be getting a hair off topic, because we're gonna get to how this works with HTTP in just a second, but I wanted you to understand just how at the core async works. So what you do is we're going to have just this static method, and this is going to be our entry point, right? So from program, we're going to call async basics.run async task. So what is it going to do? It's going to run an asynchronous task, right? So it's going to say task.run, which creates a thread and says we're going to run this thing on the thread. And then on that thread, so now we have this async keyword that's saying this method is asynchronous. Somewhere inside this method, we have to wait for something to happen, right? So whenever the async modifier is used, it has to return either task or void, right? So that way, you can't just return something, right? Because the weird part is we don't know when it's going to return, right? Like we could get into this method and it would execute, maybe the first line, and then the processor says, okay, your time's up, something else has to happen, right? So we're awaiting something to happen in this asynchronous method, right? So in this case, we're going to call greeting async, and it's kind of standard to add the keyword async after the method to say that it's an asynchronous method. So await is used before a method call, right? The method that we want to call is greeting async, but since it's an asynchronous method, we have to await for it, right? So what it does, it suspends the execution of this method, right? And it returns the operating power to whoever called it, right? So the person that called caller with async is run async task. So as soon as it hits this await keyword, it's going to say, hey, we can return and just start doing whatever the next line is. In this case, it's console.writeLine, right? So we're gonna start doing whatever this process is. In this case, it could have been like our example previously was handling weather data, right? So if we started handling all this weather data, we could let the UI keep running until it's done, and then we can return the response, right? So we absolutely must await an awaitable type. And what is an awaitable type? Well, you can see the function returns a task, and we learned about generics last week. This task happens to it happens to contain a string. We could just have an empty task, right? But in this case, we want to contain a greeting. In this case, it's just hello. So we have to, when we call await, the method signature has to have either a task or a task containing something or a custom awaitable type. We're not going to talk about those; they're way too complicated. And they're also not they're only needed in some peculiar cases. So when we execute this line, right, string result is not instantly going to be set to whatever's on the right hand side. It's only going to be set once whatever this function we're calling is done. What does this function do? It calls task.run. It's going to do the same thing that the parent did up here. It's going to run its own task. And that task is expecting that it's going to return a string. And then what do? Oh, look, we use a lambda. That lambda is going to call the function greeting, and it's going to return that value, right? So it's wrapping the string value that greeting is returned, right? It's just returning hello, right? And then we're calling thread.sleep to simulate that this thing took 2 seconds, right? If we're calling to get some sort of data, we're simulating that this data took 2 seconds to process and return, right? So at the very lowest level, that's what our function that we're trying to do is, right? We're just trying to return hello, or if it was trying to return some bigger data set, it could, right? So we're running that task, and then it's going to return the string, and then it's going to come back up here, and when it's done, it's going to set that result and print it out, right? So if we go ahead and, ooh, I remembered to close this time. If we run it, you'll see that I am waiting prints, and then 2 seconds later, hello prints, right? Because we said to go run this task, and while it's waiting on things, we can keep executing, right? So I could have duplicated this, and this guy would have just kept printing I am waiting. To however long we could have printed this out, I don't know, a billion times or something, and maybe that would take 2 seconds, and then somewhere inside of there the hello greeting would have happened. So that's async in a nutshell. We're allowing to pass the capability of continuing execution back up to whoever started me, right? All right, boys, what questions we got?
No, I guess just what happens when you have lots of tasks running. I guess there's nothing you have to do to manage that.
Yeah, that's the beautiful part about this. All the common language runtime handles all that for you under the hood. You just have to tell it, hey, go run the task, and whenever you're done, you're done.
Right, and I have like my own kind of websites up right now, just going over threading and stuff. So I'm pretty okay right now.
Okay, so we're gonna go to an example of this. And we're gonna ignore HTTP for a second, and we're gonna do asynchronous operations on I/O, so input output. In this case, we're gonna be reading from an uncompressed file at this location on my hard drive, and we're gonna be writing a compressed file, right? So what I did on the repository is in the folder, I added this file called uncompressed.txt, and if you open it up, all it is just a bunch of JSON. I just copied JSON from a website that we're going to use later, and there wasn't enough of it, so I did Control A to copy all of it, Control C, and I just Control pasted until it got to, I don't know, what's it at, 2 megabytes? So there's 2 ways that we can run this task, right? We can do it the normal way, where we just say, hey, you, compress the file, and then do, 2 tasks after it, right? In this case, in the normal operation of things, compress file, it has to compress the file before it can do the rest of the things, right? So compressing the file really what it's going to do is it's going to write it to some like weird binary format, and it's just going to be a smaller file, right? We're not going to go into compression techniques, but like the simplest one I can think of, I think it's called a dictionary compression, would let's say you have like a really long essay that you're writing, and every word the in your essay, we're gonna pull that word out, and we're gonna say, hey, we know that this spot in your essay represents the word the, but we don't want to store that memory. We'll just say you point to this thing, right? So you could see how very quickly with that approach, all duplicate words would point to something that isn't duplicated in memory, right? So the two ways that we can run it, right? We can compress the file, then do task 1, then do task 2. Or we can compress the file asynchronously, and as that file is doing its thing, we can execute task 1 and 2. Task 1 and 2 are simply just outputting the words task 1 and task 2 to the console, right? So if we look at just the normal compressed file, let's close out of some stuff. Let's keep this very simple. Compressing file, we have an input stream. So we open a file, and the input file we pass in here, right? And the input file is just um, a path, right? And we want to open the file and then read the file, right? So you can see the open function on file opens a file stream. So this is just going to be a stream, right? A stream is just like a pipe that you shove things through. In this case, the thing that we're shoving through the pipe is file data, right? So opening at a path with the specified mode. So we want to open the file and with the access, right? So the access in this case, we only want read access. We don't want write access, right? There should be only 3: read and write and read write, right? So we only want to be able to read from it. We're gonna read from the uncompressed file and write to the compressed file, right? So we have an input stream to read from the uncompressed file, and then we create an output stream, and this is going to create a file and output to that file. Then we're going to use a deflate stream, and a deflate stream is used to deflate or compress an object, right? So we're going to deflate our input stream data, and we're going to write that out to the output stream, right? You can just think of these as pipes, right? We have one pipe coming in that's our input stream. We have one pipe going out that's our output stream, and we have our deflate stream, our pipe in the middle, that's directing our input from the input stream to the output stream, right? So we're taking we have 3 pipes. Hold on, I'm gonna open up Paint so this makes a little bit more sense. We have pipe 1, pipe 2, and pipe 3. Pipe 1 is our file coming in. Pipe 2 is compressing things and then pushing them out to pipe 3, which is our output, which just writes it to a file, right? Okay, so we're just going to say input stream dot copy to, and we're going to copy everything from this stream to the deflate stream. And then the deflate stream, because we instantiated it, pointing it to the output stream, it's going to copy everything that it gets and just direct its pipe towards the output, right? So if we go ahead and run the normal tasks, we can close out of this guy, and we go back to program. So we have the run normal tasks and run async tasks. If we run normal tasks, and we hit run, you can see, did I not close out of the console? I don't think I closed out of the console. Okay, so task 1 and task 2 almost immediately finish. So what I want to show here is if I go to the uncompressed file, and I don't know, I'll just copy all of it and paste it a couple more times. So now the file is, I don't know, 11 megabytes. We'll see if that takes a little bit longer. And if I open up the compressed file, you can just see it looks like a bunch of gobbledygook. This is what binary files look like. These aren't human readable. Basically, what it does is it like takes the literal like binary data, and like normally you'd say like like 0001 is equal to A, 0002 is equal to B. Well, in this case, it turns it into these ugly characters that happen to be compressed. Okay, so now our uncompressed data is a little bit longer, so this should take longer, right? So you can see it takes a second. Oh, still doesn't take very long. All right, we'll go copy paste it some more. Okay, so now it's 50 megabytes. Maybe my computer's too fast. Still too fast. I'm trying to simulate this thing taking a little while, right? Now we should be at about 150 megabytes. 140. Okay, this should take a second and show you that it's... Okay, so you start the program, it takes a second, and then it does task 1 and task 2, right? Whereas, if we do the asynchronous way of doing things, it will start decompressing the file, or it will start compressing the file, and then immediately do task 1 and task 2, as that's still compressing, right? Another way to show this would be that whenever the file compression is done, we could say console.writeLine compression is done. And we will go ahead and put that in our async method as well. So our async method looks very similar, right? It uses the 3 streams, but instead of just copying to the deflate stream, it await, right? We wait for this function to be done before we keep going. And then closing the streams just means we don't have this pipe open anymore. We're not storing memory for it. So these 3 lines won't execute until this one is done. However, since this is a task, the other lines can execute, right? So if we run the non-asynchronous task, you'll see that compression has to be done before task 1 and task 2 can go. However, in async, task 1 and task 2 print out, and then whenever compression is done, right? Like we don't care when the file is done compressing, we just want it to be done. So the only really difference that you're going to notice is that your function has to return a task, it has to have the async keyword, and whatever thing is going to take a while, you want to use await on. And you can see copy to async is actually a task itself, right? Okay, so how does this apply to anything? HTTP is our application case. So in HTTP stands for Hypertext Transfer Protocol. Hypertext was the old way. I don't want to say old. Is the way that data is transferred across the web. A hypertext, you can think of it kind of like a hyperlink, right? Hyper meaning like a hyperlink goes to the next thing, right? So like hypertext is text that includes hyperlinks, right? So what does an HTTP request look like? Well, I found this handy dandy website called jasonplaceholder.typeofcode.com, and what it does, if you just scroll up to the top, it's a fake online REST API for testing and prototyping. So it's a fake API, meaning that it just holds dummy data. It's a REST API, meaning that you can make REST requests, and well, I'll show you how they're formatted in just a second. And an API just means that it's a server that you can send some sort of request and receive some sort of data that you're looking for. There are different kinds of APIs. This is an API to receive data over the web. A different type of API would be an operating system API, right? There's specific commands that you can run on Windows itself to create and read and open a file. There's also APIs to access another application, right? So like on the OneLeaf website, we have an API for you to be able to create a user or log in. That would be an API, right? So an API is kind of a term. I know this is a term that I had struggle conceptually understanding, because an API really does encompass a lot of things. API stands for Application Program Interface, and I think it's beautiful that we talked about interfaces last week, because what conceptually is an interface? An interface provides a medium of communication between two completely disparate things. The interfaces that we talked about last week, for example, an interface called flying could be the common ground between an airplane and a bird who don't have anything in common. For example, another example would be a mouse, a keyboard, and a monitor would be interfaces to be using a computer, right? You can operate a computer from the command line, right? Without like you could remove an interface, like you could remove the mouse and you would still have this interface, right? So an API is an interface between your program and some data. That data could be uh, the operating system itself, right? So you could have an API between your program and trying to create a file on the operating system, or it could be between your front end, right? So like my website could have a login button, and you needed an API on the back end that would allow you to send a request to log in. So what does this website do? It just holds some placeholder data, right? So if we scroll down, you can see here are its routes or endpoints. Basically, what they are is if I click on /post, you can see what does it contain. It holds 100 posts. So if I just click on it, I'm going to open it in a new tab. So you can see it looks like JSON, right? It has the curly bracket or the regular bracket to show that it's an array. and then the curly brackets for each one of them. So what does a post hold? A post has a user ID for the user that posted it. It has a unique ID for the post itself. A post has a title and a post has a body, right? And you can see the API has /posts appended to the end of the URL. So if we break down URLs, they're typically either HTTP or HTTPS. S is for secure, right? It means when you send a request over the network, your request is encrypted. Then you have the host, right? If you're running it on your computer yourself, it's localhost. If it's on Google, it'd be google.com. That would be the host. And then once you get to that server, then you got to tell it where you want to go. In this case, it would be /posts. So we're going to go over a little visual representation of how the internet works. I feel like I should have made a separate post for this, but we'll go ahead and add it to this stream. So you are on your computer, right? And you hit the enter key after typing in google.com. So what happens? You're going to have your PC, right? We're going to call it your tower or your PC or whatnot. And so it goes out of your Ethernet cable or over Wi-Fi to your router/modem. And I believe it's your modem that actually sends the network request to your ISP. So if you have Comcast, CenturyLink, Cox, ISP stands for Internet Service Provider. And then your Internet Service Provider goes out to DNSs, and these are domain name servers. And so these are just really big lookup tables that says if you go to google.com, let's send you to IP address 66.11.whatever. And so what happens is, right, so let's walk through this process one more time. You hit enter on Google, it sends it to your router at your house. Your router sends that to your ISP, usually through like a cabled network. Your ISP is connected to DNSs somehow, right? And then the DNS kind of acts as like the postal service, right? You give your letter to the postal service in I don't know, New Jersey. And then the postal service says, okay, let's go give this letter to the postal service in, I don't know, maybe you're trying to get to California or whatnot. It flies that letter over to Arizona, and then Arizona handles getting it to California, and then California handles getting it to the city, and then the city handles getting it to, I don't know, your neighborhood, and then your neighborhood has a postal service or whatnot, right? So the DNS is kind of like a big network of people that happen to know about people, or servers that happen to know about servers, right? And so eventually, somewhere in the DNS network, it'll find google.com servers, right? So you get to Google. And so when you get to Google, if you just say google.com, it has to know what to send you back, right? So this is the request and response that I'm talking about. You send a request, and we're just going to give it a big arrow, and you request google.com. What does it send you back? If we go to google.com, it sends you back a web page, right? If you open up the developer tools on most browsers, it's Control-Shift-I, and I refresh the page, you can see over network, you can see all the things it's sending me, right? It's sending me back like a JavaScript file called API.js. It's sending me some photos that would correspond to the photos here, and then it's sending me like an HTML file, right? And the HTML would contain the data for this. It's also sending me CSS to structure it and whatnot. In this case, all this web page is sending back is unformatted JSON, right? It's not sending back HTML or anything. An API just sends you back data, whereas a website or a web server would send you back, an actual a web page, right? So that was a really long-winded answer to explain why we're talking about HTTP. So thank you. So in C#, everything is kind of handled for you by this HTTP client, right? So you have a client and a server. A client makes requests. In general, a client makes requests and server sends responses, right? So the HTTP client sends a request and receives a response. And you can see that when I'm hovering over it. HTTP client comes from system.net. Net stands for networking. .http. So we have this function called download. And all we want to do is download the home page for something. So we're going to create a task. and I'm just going to have it return a string corresponding to whatever we're downloading. So we're gonna say our task is running the function main request. So I could have done task.run instead of this formatting. These are just different syntaxes to do these things. So if we format this into the syntax that we were using earlier, it would be, yeah, this guy does it the same. It just creates a task and assigns it the method. I believe it was the Async Basics that used task.run. Yes. So they do the same thing, right? There's different syntax. So the task that we want to run is main request. Well, what does it do? It's going to call, it's going to use asynchronous network methods, and it has a try catch block. We talked about these because what happens if the HTTP request has an error, right? What if we try and reach google.com but it doesn't exist? Or what happens if we reach google.com and the data that we're trying to send it is bad and they don't know what to do with it, right? Let's say we're trying to like go to google.com/images and we'd want to pass it in like an image name and it doesn't know what the image name is, so it'll have to return us some sort of error. So we say client, the HTTP client that we get, it's a static field because we only want one HTTP client, right? The client is responsible for sending us requests and responses. We only want one client because it can handle multiple requests and responses because it's asynchronous, right? So we're going to get async. So it sends a get request to a URI, a unique resource indicator, uniform resource indicator. I forget what it stands for. URI is a more generic URL, right? So a URL would be a basically it's a path to a unique resource is what it is. In this case, our unique resource is google.com, right? So when I get back the response, right, so I'm waiting for Google to send it back to me, right? So I'm waiting in this picture. I'm waiting until this arrow gets all the way back to my computer, right? So once it gets back to me, I fill in my response message. I ensure the success status code, and we'll talk about how HTTP messages are formatted here in just a second. So I make sure that it has a successful status code, meaning that Google could return me that page. And then all I do is from that response, I get the content inside of it. And I just read that string asynchronously, right? And I'm doing it asynchronously again because what happens if it's a really long string? I want to be able to keep executing things outside of it, right? And I did note here that these three lines they could be replaced by just get the string async rather than getting the response, ensuring the success code, and getting the string. But I wanted to give you a step-by-step of what's happening. And then once we have the response body, once we have the string that represents the page, we're just going to return that, right? And so now our download homepage task holds a result, right? So the response, we have to access the result of the task to actually get to the response of the request. And then we're just going to write it out, right? And then if we were to hit an error, we would have printed out exception caught and print the message. So if we just go ahead, let me close out of the console so it prints. If we go ahead and hit run, you'll see I am dumb. Yeah, that's what we'll see. If we go back to program, I didn't uncomment out that method. You're going to see a bunch of gobbledygook. And if you know anything about HTML, you'll see that this is formatted HTML if I kind of blow it up here. You'll see it starts with an HTML tag and then it has a body and whatnot. So when we request from Google, it's returning us an HTML page, right? Like if I go into here and I copy all this and I create a new, come here, come on. Okay, it's not in there. If we go to Notepad++, and we create a new file and we paste in this HTML file, and I save it, and I'm just gonna save it as Google, and you have to save it as a .html. If I write, it didn't save it as .html. Whoops. See how it like uses the Google logo when I save it as an HTML file? If I double click it, it'll open in Google, right? And you can see that it has all of the links and whatnot that Google would have, but the URL is to my computer, right? So a web page is represented by a certain set of data, right? And then the actual functionality depends on the JavaScript that's on the page, right? So if I click on these things, it will actually take me to that link because the JavaScript said so, right? The JavaScript actually held the link to that google.com page. So we're going to look at how HTTP requests look next. So I have this application called Postman. I believe it's free up to some point. There's lots of applications out there like Postman. It's basically a way to test APIs, right? And a way to format requests. So I'm gonna. Okay, so I have two requests, right? So I created a collection of requests called JSON placeholder, and the first one is just going to be called get posts, and we're going to make a get request saying I want to get some data from /posts, and if I hit send, you'll see that it sends, and it prints out that same data that we were looking at when we hit /posts, right? Postman just adds some syntax highlighting so it's colored, right? Well, in the HTTP request, it has some extra things inside of it, right? So you can see you can add query parameters. We'll get to those in just a second. You can add authorization, right? So like if you had a username and password. And then it has headers, right? Headers basically say, you could say the user agent. So in Chrome's case, the user agent would be Chrome or it could be Firefox. In this case, it would be Postman. You can tell it what type of data it accepts. So it could be HTML, JSON, so on. Whether or not it wants to cache data. Caching meaning it'll save it off for next time. It has a token, a host, and so on, right? So when we send a request, it has a body, right? A body is like the data that we're sending. In this case, we're not sending any data, but in our headers, it's sending like metadata, right? Like some extra things that the server will want to know how to handle this request. So you can see if we go to our body, we have no body. I have no body. But it still returns us data, right? So this is printed out pretty. If I go to raw, you can see it's just raw JSON data. So the next request that I made, if we go back to their API, most APIs have some sort of documentation that explains how things work. In this case, I went down here, and you could see you can make a GET request to /posts. You can make a GET request to posts/1. So if I go to posts/1, it only returns me the posts with ID 1, right? So the backend, their server, handles what happens when you get this request, but their API tells us how to access that data, right? We want to access the post with ID 1, so we pass in post/1. And then maybe want to get only the comments on that post, so you could do /comments. And you can see there are IDs for the comments, right? And then there are these things called query parameters, right? So I want to query the data, right? So I want to say, I want to get posts where the user ID is 1. I don't want to get the posts where the post ID is 1. Most things are based off of IDs, right? So the first user to sign up on your website would be user ID 1. The second user would be user ID 2, and so on. Most databases handle those things for you. So the question mark means that I'm going to start saying query parameters. And so I have the name of the parameter, user ID, and the value of it, 1. So if I go to Postman, I have this GET request, and it's going to go to JSONPlaceholder.com, and it's going to go to /posts, and it's going to give the query parameter that user ID equals 1. So if I hit send, it's going to get all the posts that basically what this is returning is all the posts that were created by the first user who made an account on their system, right? Okay. So that should give you a decent idea of how HTTP requests work and how to get them from an API, right? So now we could, there's a billion different ways we could go about this, right? We could use the JSON placeholder and grab more data from theirs and figure out how to format it and what to do with it. We could just look up like free APIs, and there's a GitHub repo with a bunch of free APIs, right? So you could access I don't know, one that I was looking at the other day was this food and drink API called the Cocktail Database. And it has a list of ingredients for cocktails and making alcoholic drinks and whatnot. And I was thinking of making an app that would make a request to their API that would include the ingredients that I have at my house for a drink. And it would return to me all of the drinks that are possibly made with those ingredients, right? Like let's say I have, I don't know, lime juice and ginger ale. It would say, okay, here's all the drinks that you could make with that, right? So that's kind of like some cool things that you can do with APIs. Something to consider when you're doing APIs is you can see there's three different extra things it adds about the API, right? It has the name of the API, the description, whether or not it requires authorization. So some of them don't, and some of them require an API key. And usually, whenever you want to use an API, they require some sort of key. And usually it's just some randomly generated key. And you can see on the JSON placeholder, if I scroll, where was it? I don't think they require an API key if that's what it was. Oh, okay. We'll go to the cocktail database. I have them bookmarked. You can see they have some ugly documentation, but you can see you can use the test API key 1 during development, right? So like they might limit the test API key to um, like I don't know 1,000 requests a day or something like that, and after that you're kind of screwed. And then sometimes they'll make you like pay for an API key, right? So the way actually hold on, let me open that back up. The way they do it, right, is you go to their URL, you access /API, and then we want the data formatted in JSON. Then we want version 1 of the website, and then we pass in our API key. And then they have search.php for the page that you reach, and then the query parameter would be $I for ingredient, and then the ingredient is vodka. Or in this case, you can search cocktail by name, right? So you could pass in the query parameter S. I don't know what that stands for, but margarita. And so on and so on, right? So we can go lots of different places with all the APIs that are out there, but I'm hoping that covered the very basics of how HTTP and APIs work. What questions do you guys have? We could go just about anywhere from here.
I've used APIs a bit before,
What's that?
so I didn't really have any questions
Oh, okay.
regarding the APIs, but I think I did have some questions about like threading and stuff that we did.
Yeah, sure. Go for it.
So could you have like a sort of a thread within a thread? So like the thread like makes a thread basically.
Yeah.
Yeah. So is there any sort of constraints on that?
So when it makes a new thread, it's just like a completely separate call stack, right?
Yeah.
The only
Okay.
constraint is like your computer has enough cores to handle the operation of those threads, right?
All right. I got you. Yeah. So it's pretty much. Yeah.
But even if you make too many threads, they just may not be given CPU time to work because there's too many threads already executing, right?
Right. I got you. Yeah. And that's all handled by thread pool. Yeah. Yeah. That makes sense. I really need to play around until it kind of sinks in. But yeah, it was the threading that was more sort of complicated for me than the sort of requests to the server and that.
Yeah, I think I need to make a like a how the internet works series that's kind of separate, independent from languages.
Networking 101.
Mm-hmm.
Yeah, man. Yeah.
Um, any other questions?
No, I'm okay.
I was wondering about the throughput and whether you could
Like
actually like sort of print at the screen, or if it's like saved as like a bit of state or something, and access
print
that.
out what the throughput is?
Yeah, just like a point in time, the throughput currently. It's kind of a random
Uh,
question, but
I can't think of a way to measure throughput based on threads. I feel like there's probably something like, I don't know, is there something in like system.environment? That's a really good question.
I was just kind of curious. That sort of practically helpful, but yeah.
I assume I assume it would almost be more pain than it's worth to know what the throughput is, because you'd have to like measure everything, which would make it take longer and make it seem like it's longer than it is, right?
Yeah, okay, but it must have to be measured, you know, behind the scenes anyway, right? I
Hmm.
thought, but it might not be sort of an accessible property or whatever.
Yeah, I feel like it would almost be something that you'd have to measure theoretically, right? Like you could measure like the number of threads that are started and destroyed in a certain amount of time based on like how long the process is taking.
Yeah, okay.
Hmm. Typically, like the measure of throughput that comes to mind for me would be bandwidth, right? Like if you measure the level or the level of network bandwidth that you're using, right? If all your methods are HTTP methods, right? You could measure how much your um, throughput is based on how much network bandwidth you're using. But to measure the actual like computational throughput that your computer is using, it would kind of depend on which like what data you're working with. So that's all I had planned for this stream. I do have some articles that would be good for you guys to read. I will post them in the streaming discussion channel. I feel like our description is already has a lot of stuff in it. So if you find this video afterwards and are interested in some useful articles, message me in the Discord. So next week what we're gonna do is we're gonna leverage. I feel like I'm going almost too deep into the weeds here. So what I want to start doing is I want to start building up a web server that's going to act as an API that we can use to do things, right? So over the next week, I will chit chat with the people in OneLeaf and see what sounds fun. We could make, a weather API. We could do that cocktail one and just make a front end for it, right? So like, we'd receive the data for the cocktails, and we'd make a front end that would display a picture of the cocktail and show its ingredients like nicely formatted rather than in that ugly JSON, right? Um, or we could, I don't know, we could make a simple CRUD application. That's probably what we would end up doing. CRUD stands for create, read, update, and delete, right? So we'd have some database that would hold like, I don't know, posts, and you could create a post. You could read the posts like on a page. You could update a post, like change the title or something, or you could delete a post, right? So that's CRUD is like the most simple interactability or most simple operations you can perform on an API. Um, But yeah, so we'll start with next week. We'll start looking at making an ASP.NET application and making some sort of CRUD interface. I think it'll just be an empty database, right? We're not going to reach into somebody else's API. We'll just start with an empty database, and we could put in like some dummy data that we could like, I don't know. We'll just have like a text file that stores some JSON data that we can populate the database with. There may be a week break of this stream for me to make sure I prepare that and have it high quality, because I don't want to skimp on the quality, because there is going to be a lot to cover when just like creating the project, for example, and knowing what everything does. But as far as this week goes, are you guys both clear on everything that we talked about? We just barely scratched the surface on HTTP, and I know, Max, that you have some experience with it, so it may make more sense. But I'm sure, Alex, you're kind of lost.
I mean, that's been my thing throughout this entire process. I mean, throughout the days, I'll just kind of mess around with it and kind of go over what we've learned in the stream. So by the time like next week rolls around, it won't be such a foreign concept to me. So I'm pretty used to it. Like after the stream, not really getting it, but by the time next week rolls around, I'm pretty okay.
And that's kind of my goal, is not to teach you every little thing, but my goal is really to give you guys an idea of what you even need to research and what you guys can Google, um, so that way you can kind of learn these things on your own. Because I'm sure other people would do a much better job of some of the topics than I would, and I just don't have the time to teach everything.
Right, and you know me, I'll usually go into my own rabbit hole and emerge a couple days later after looking at another topic because I'll kind of pull everything apart one at a time.
Yeah, exactly. So yeah, my goal really next is to start working on a project so that all these concepts can start making sense in context of what we're working on. And my goal is going to be to come up with an idea and walk you guys through the steps and why I make the decisions that I make. Why why we choose one process over another. To really give you guys some insight on how these things will work at a higher level. So yeah, I feel like the stream was a lot shorter this week. I didn't have a ton left. Like if you guys have stayed through the stream so far, and you started out understanding everything, and you've gotten to the point that you guys have a pretty good understanding of C# as a language itself. Now it's time to talk about applications of the language and what you can do with it. So my goal is to keep this stream more on the professional side of things, talking about helping people in OneLeaf be able to get a job and be proficient with C#. So we're going to look at ASP.NET. But once we're done with the ASP.NET stuff, I'm going to be looking at making games in Unity, and I'm hoping that'll be a series that I will probably keep up long after, because it won't be so much teaching as it will be almost streaming me working on things that I'm interested in. But
Sounds like a good plan, mate.
alrighty, guys. Well, I appreciate you two coming on the stream, and I appreciate everybody else that's watching. If you guys have any questions, as always, hit me up in the Discord.
Yeah, sweet. Maybe just put the those articles that you mentioned.
Yeah, I'll put them in the Discord in just a sec.
Lovely.
Alrighty, bye everybody. Thanks for watching.